In 1975, Gordon E. Moore, the co-founder of Intel, stated that the number of transistors on an integrated circuit board must double every 2 years. So if the size of the integrated circuit board is not changing, how can so many transistors fit on such a circuit board? Well, the solution to this is nanotechnology. Nanotechnology in today's world is used in many different aspects as it comes to CDs, car waxes, clothing, etc. But also it involves polymers. The use of nanotechnology involves the process of electrospinning, which we will talk about further in our presentation. Our group, the Nano Group, consists of Jeremy Gruber, Randy Grimm, and Ryan Schultz. And we will talk about the unique qualities that allow different polymers to be electrospun and their different applications in today's world. I, Ryan Schultz, will talk about the history of electrospinning as well as the process of electrospinning. And Jeremy Gruber and Randy Grimm will tackle the applications of the modern world and its future uses, where Jeremy Gruber will talk about the biological field and personal safety, and Randy Grimm will talk about energy and environment. The process of electrospinning can be dated back as the late 1500s, where Sir William Gilbert first realized the phenomenon of applying an electric current to a water droplet, that it formed the shape of a cone being shot across a certain distance. It wasn't until 1902 that J.F. Cooley and W.J. Morton first patented the electrospinning process and the apparatus that they created. In the 1990s, electrospinning became really popular with the Rennecker Group and his multiple processes for the application of electrospinning. And electrospinning has become very dominant in the present day, as you can see from the graph that many patents and publications have been cited in the field of electrospinning in certain applications in today, and it will only grow into the future. An electrospinning station consists of a high voltage power supply, syringe with a needle, a syringe pump, a collection plate, a heat source, and a polymer solution. A polymer solution is created by mixing a desired polymer, for example polycaprolactone or polyvinyl alcohol, with a solvent of known solubility. The polymer solution can be altered by changing the weight percent of the solid polymer going into solvent. This altercation changes the viscosity of the solution and then by affecting the size of the electrospun fibers. Different additives can be mixed into the solution depending on the certain environment that it is to be tested. For example, silver nitrate can be added to polyvinyl alcohol to test antibacterial properties within a cell culture. Other variables can be changed based on what is desired. Voltage can be increased or decreased to speed up time the polymer makes it to the collection plate. The distance between the syringe and the collection plate can also be changed. Also, for viscous solutions, the pump rate can be increased to allow the polymer to make it past the needle. Usually the electrospinning process is run until the syringe runs out of polymer, but time of spinning can be adjusted depending on the desired mat size. With all parameters set, the process of electrospinning can start. The voltage is adjusted until the Taylor cone appears. This cone is seen at the edge of the needle and is the only visible part of the solution that can be seen other than within the needle. Solvent is evaporated into the air from the use of the heat lamp, which leads to the collection of solid fibers on the ground surface. After your desired time is up for spinning, as you can see on the left, a finished mat of electrospun fibers is produced on your collection plate. Further analysis seen on the right under a scanning electron microscope shows the fibers cross-linked and not properly straight aligned. This is due to the whipping sensation that comes off of the Taylor cone as the polymer moves through the air to the collection plate. Further analysis of the polymer can be done by mass spectroscopy and elemental analysis, where you can see certain elements that are present within your polymer solution on the mat. And now Jeremy Gruber will talk about the applications of polymers as they apply to the biomedical and safety field.
Thank you, Ryan. So, electrospun nanofibers have a wide array of applications throughout the biomedical field. Both synthetic and natural polymers are capable of being electrospun to precise dimensions and specific attributes to really hone their morphology and function. These fibers can be involved in tissue repair, controlled drug transport, medical device implant, and many, many more. To begin, I'll discuss tissue regeneration and repair. So as you see on the image in the top right, shown is a picture of electrospun nanofibers, which are shown in green, and then the red spots are cultured muscle cells. You see that these cultured muscle cells really attract the nanofibers because the fibrous nature of these electrospun polymers really mimic the extracellular matrix in the fibers that hold the tissues within the body together. The biocompatibility of these fibers can be tested outside of the body by culturing the organ-specific cells and then evaluating their growth. What this does is it can provide a sort of scaffolding for injuries. This overcomes the need for donor tissue. So, for an example, for burn victims, rather than having a skin graft put on from another part of your body or from a donor tissue, electrospun polymer can be placed over the injury as a sort of artificial skin. What this will do is it'll just cover the wound and allow for the human body to generate its own skin over that, while the artificial skin just sort of acts to provide structure. So this fiber scaffold can be designed to have antiseptic properties that would prevent infections while the body heals, and it can also be designed to have these sort of genes or enzymes in it that promote cellular growth so as to hasten the healing process. Another aspect of an application of electrospun nanofibers in the biomedical field is with medical implants. So these fibers can be designed with many mechanical properties in mind to have a certain rigidity or flexibility or any of that sort of stuff, or durability, so as to have the right application within the human body. Pictured in the top left, you'll see an image of arterial stents. So these stents are basically inserted into an artery that is defective or underdeveloped so as to provide support to promote healthy blood flow. These arterial stents need a balance of flexibility and rigidity so as to provide enough support so that it keeps the artery walls open but still flexible enough for the movements of the human body. So approximately 40,000 children every year are born with a congenital heart defect. These stents can be designed to biodegrade gradually so that as the body develops and grows and strengthens around that area, the body will no longer have a need for that stent. Also, if heart disease is an issue, these stents can be designed to have a sort of agent that combats plaque buildup for people, at-risk areas of people with heart disease. So what this will do is it will help remove plaque from the arterial walls and promote healthy living for as long as possible. Other applications of medical implants include dental implants, where high durability, strength, and antimicrobial properties are required, or in artificial ligaments associated with sports-related injuries. On the pharmaceutical side, electrospun polymers can be used to act as sort of smart drugs. These polymers can be covalently bonded with drugs or targeting ligands and groups so that they can attack a certain cell and reside there until a certain drug needs to be delivered. So an example of this could be shown in the bottom, where you have your polymer backbone covalently bonded with a targeting moiety and a drug. Say that the bond between the drug and the polymer backbone is pH sensitive, and this entire drug is added to the body where it targets a certain cell. If this cell drops below a certain pH, the drug will be released into the cytoplasm, where it can work to maintain the proper equilibrium within the cell. This is a great aspect of smart medicine, where you can target specific areas of the human body to treat or diagnose illnesses or injuries, that sort of stuff. Obviously, a huge area for this application is with cancer, where you can design specific drugs to target cells that are cancerous, and have drugs that go straight to these cells and render them inert or kill the cells. Next, I'll talk about the usage of nanofibers in protective clothing and equipment that can be used to detect and neutralize hazards before they come in contact with the body. So, soldiers, firefighters, medical personnel, and other professions of that sort require a high level of protection from biological and chemical hazards in their daily life. So they use these special suits, some of them are hazmat suits, that protect them from a variety of these toxins. However, hazmat suits are traditionally bulky, inflexible, not very breathable, they do not protect the body from all ranges of hazards. These suits cannot be worn at all times due to their lack of comfort and breathability, so it takes time to put on your firefighter's gear or that sort of stuff, which really is not great in case of an emergency, because in an emergency, time is the overwhelming aspect. A solution to these problems is the implementation of smart clothing and protective equipment created from electrospun nanofibers. So this smart clothing is capable of sensing harmful substances and then protecting the body from these substances either via filtration or decomposition of the active species. Nanofibers can be designed with detection software that can alert the wearer of all sorts of toxins from carbon monoxide to biological weaponry. So a study at the University of Tennessee created and analyzed the properties of electrospun cellulose acetate, where it's covalently bonded with an enzyme that degrades organophosphorus agents in the air. So here they discuss the fact that electrospun nonwovens are much more breathable, lightweight than traditional woven textiles. And the opportunity to covalently bond functional groups that can render harmful bio and chemical agents inert is a great application for this. This would be a great aspect to be used in gas masks, where you can make them much more smaller and lightweight, where it only has to cover the mouth, rather than that large traditional gas mask we see in war movies and that sort of stuff. Applications of these technologies are endless, from coating a soldier's body armor that alerts the soldier about the presence of a biological or chemical warfare agent, towards even making a bed sheet out of this non-woven material that will vibrate or alarm when there's carbon monoxide levels detected too high within the house, thus protecting the family. So the image in the bottom right you can see is the reaction of mustard gas with the human body. So mustard gas is a chemical warfare agent used back in World War I, which binds to the DNA and ultimately kills the cell. So using amines or other active materials like oximes inside the woven smart clothing will be able to decompose the mustard gas before it reaches the human body. So this concludes my discussion of electrospun fibers being used in the biomedical field as well as smart clothing. Now I'll be turning over the presentation to Randy Grimm, where she'll discuss the applications of electrospun nanofibers in energy and the environmental field.
Thank you, Jeremy. Now that you have heard a bit about how electrospun nanofibers are used in defense and biomedical applications, I will now discuss their importance in biotechnology, environmental, and energy industries. As many of you know, water pollution is a very widespread issue that affects many countries around the world. In fact, 3,575,000 people die every year from water-related diseases caused by water pollution. Heavy metals such as lead, mercury, and copper often flow from industries into the waterways that surround them, as shown in the picture on the screen. Electrospun nanofibers can be used to create affinity or absorptive membranes that can eliminate or recycle these heavy metals to decrease water pollution. The polymer nanofibers used in these membranes are functionalized with ceramic nanomaterials such as alumina hydroxide or iron oxide, which attract heavy metal ions by absorption or electrostatic attraction mechanisms, thus removing them from the water. Water is much more sensitive, however, to inorganic molecules than heavy metals. Although inorganic molecules make up only 1% of water pollutants, they use up the dissolved oxygen in the water, thus making it difficult for water to sustain life. Beta-cyclodextrin has been introduced into polymethyl methacrylate nanofiber membranes to develop an affinity membrane for organic waste removal. Beta-cyclodextrin is comprised of 7 glucose units and has a structure with a hydrophobic interior and hydrophilic exterior, which pulls hydrophobic organic contaminants out of the water. Electrospun affinity membranes are also important in the biotechnology field for the purpose of protein purification and toxin removal from bioproducts. Affinity membranes capture a specific target molecule or ligand by immobilizing a specific capturing agent or ligand onto the membrane surface. These ligand molecules must be covalently bonded to the surface of the electrospun membrane. An example of this is shown in the pictures on the screen, in which cellulose nanofiber membranes have been surface functionalized with the dye cyberchron blue for the purification of albumin, which is the main protein of human blood plasma. Natural energy sources such as crude oil, natural gas, and uranium power most of the world we live in today, but they are causing serious damage to our environment. These sources release enormous amounts of carbon dioxide, which is the most significant contributor to climate change. Electrospun nanofibers can play a huge role in advancing sources of alternative energy such as polymer batteries, fuel cells, photovoltaic cells, wind power generators, and geothermal power generators. Polymer batteries are the batteries used in cell phones and PC notebooks to replace the typical bulky lithium batteries. An example of a lithium-ion battery is shown on the screen in the bottom right corner. These polymer batteries consist of a carbon anode, lithium cobalt oxide cathode, and polymer gel electrolyte as shown in the picture on the screen. Lithium ions move toward the anode during charging and back toward the cathode while discharging. These polymer batteries allow less electrolyte leakage, high dimension flexibility, and high energy density per weight, but the energy density per weight still needs to be increased to increase the market share of these batteries. This problem is being solved using polyvinylidene fluoride, or PVDF, nanofiber membranes to assemble a new polymer battery. The porous structure of this nanofiber membrane allows very high lithium electrolyte uptake, which reduces the amount of leakage from the battery. This also allows for thinner battery packs to hold a much larger amount of electrolytes, which is very important as technology continues to decrease in size. The large surface area of this nanofiber membrane also enhances ion conductivity. Thus, polymer batteries constructed from nanofiber membranes will have a higher energy density per weight than typical polymer batteries. Proton exchange membrane fuel cells, or PEMFCs, are a type of fuel cell being developed for transport applications as well as for stationary and portable fuel cell applications. Electrical generation occurs in these fuel cells via a chemical reaction between the hydrogen at the anode and oxygen at the cathode. The important thing about these fuel cells is their ability to operate at very low temperatures, which is about 100 degrees below Celsius, and the fact that their electrical output can be tailored to meet specific power requirements. As shown in the image on the screen, protons are transmitted through an electrolyte membrane that contains distilled water, while electrons move from the anode to the cathode. Electrolyte membranes used in these fuel cells should have high proton conductivity, shielding of electron transport, and water retention to be able to hold the distilled water. Nafion is a perfluorosulfonic acid polymer film created by DuPont that has been used for these purposes so far, but they are expensive at a cost of $800 per kilogram. Electrospun nanofiber membranes would be able to decrease this cost due to their ability to produce the same amount of surface area without using nearly as much material. The porous structure of these membranes also have the ability to hold water, which can increase proton conductivity. I will now hand the presentation over to Jeremy to conclude the discussion of electrospun nanofibers.
Thank you, Randy, for that very interesting discussion about energy, biotechnology, and the environment applied to nanofibers. To summarize, the unique qualities of electrospun nanofibers allow them to be viable solutions to many of society's current issues. The presentation began with Ryan Schultz discussing the history and background and the actual process of creating these electrospun nanofibers. From there, Jeremy Gruber discussed how electrospun nanofibers can be applied towards the biomedical field as well as into smart, wearable, or defense products. Finally, Randy discussed the applications of nanofibers in the energy field, biotechnology, as well as in the environment. Overall, electrospun nanofibers are a very interesting topic with applications that can span an entire realm of possibilities, and future research can only help these products grow and develop into possible solutions for the entire world.